for today, as you see here, the title of the talk is Restriction on Hazardous Substance, which in fact we call it the ROHS, by Dr. Don Estreich from Agilent Technology. So let me now read about Dr. Donald Estreich is currently ROHS coordinator of the Advanced Development Group in the Technology and Services Organization of Agilent Technologies Incorporated in Santa Rosa, California. He received his Bachelor of Science in Electrical Engineering from University of California, Berkeley, and the Master of Science in Electrical Engineering and PhD from Stanford University. Dr. Estreich is an adjunct professor of our department, that's the Engineering Science Department, and he has worked as a gallium arsenide integrated circuit design engineer, later managing the IC design group, next the IC product engineering group, and more recently he managed a package and interconnect group serving instrumentation applications. He has served as chairman of the Industrial Advisory Board to the National Science Foundation sponsored Packaging Research Center at Georgia Tech, and is presently a member of the Board of Advisors to Electrical Engineering and Computer Science Department at UC Davis. So here is Don.
Thank you, Ollie. Well, the topic today is on restriction of hazardous substances. And the question you might be asking is, why do you care? Well, if you're in electronics, and, for example, you have something to do with hardware, such as printed circuit boards, you care about this because it actually makes life a little more challenging in designing and building and recycling some of these products. So what I'm going to do is first tell you a little bit about regulatory affairs, and then second I want to talk about how it's impacted the printed circuit board world, printed circuit assembly, with lead-free solder. And that will be the engineering part of it. But first we're going to talk a little bit about regulatory affairs. Okay, so as I point out here, regulation is really a way of life. You probably are all aware that you no longer use lead in your gasoline in automobiles. That was outlawed some time ago. Lead was removed from paint and pencil lead. Asbestos. A lot of efforts going into removing asbestos in various buildings. So regulation actually has a lot of impact on us. And regulation has a lot of very interesting aspects to it. For example, well, what are you going to regulate? I mean, there are a lot of substances, a lot of chemicals out there. I'll guarantee you a lot of them are not very healthy, especially if you ingest them. And so the question is, what do you regulate? What is involved in regulating it? What kinds of economic consequences are involved? When you decide to regulate something, it doesn't just happen immediately. There's a lot of change that has to occur, and it can take a period of years before some of these laws really become effective. There's cost, how you enforce regulation, those kinds of things. So we'll talk a little bit about that. I went back a little bit in history, and I'm not going to talk about any of these laws, incidentally, but there have been literally hundreds of pieces of legislation that have been passed by the United States Congress regulating chemicals, substances, the environment. This is just a partial list, and incidentally, the EPA was established in 1970 by executive order. So some of these pieces of legislation go back before the EPA, and of course the EPA is very active today. So a lot of things are being looked at and regulated, such as water supply, etc. We're not going to talk about these. The one I want to talk about is the regulatory activity in the European Union. They've been very effective, they've been very proactive in Europe in regulating hazardous substances. And the program I really want to emphasize here is this ROHS program, Restriction on Hazardous Substances. We sometimes just call it ROHS for short, because they get tired of saying Restriction on Hazardous Substances, quite frankly. But to put this in context, back in the 1990s, the European Union decided, well, it needed to regulate batteries, because if you've ever had a lead-acid battery tip over in your car trunk when you were trying to transport it and acid spilled out, you know there's a hazard here, and there's a lot of lead in batteries. So they got involved in regulation of batteries, packaging materials, and then in after 2000, they became very active in things such as end of life of vehicles, regulating substances that go into vehicles and the recycling of those substances. There was an initiative called the Waste on Electrical and Electronic Equipment, the Wii Initiative, and that's very nicely coupled with the Restriction on Hazardous Substance Directive. This is a recycling initiative. This one attempts to address the manufacturing and the substances that go into these. Now, there are a lot of other programs, such as there's a new battery directive in Europe that's more effective than the old ones. They've learned a lot. There's a program called the Integrated Product Policy, Energy Using Products. There's a new one that is called REACH, Registration, Evaluation, Authorization, and Restriction of Chemical Substances, and that one's just being dealt with now. And there's talk about halogen-free, for example, in PC boards, sustainable manufacturing, and things like that. It turns out that this Directive 2002-95-EC, or the ROHS initiative, actually became effective in 2006 for a number of products, such as cell phones, laptops, all sorts of consumer electronics was impacted by this ROHS program. And that's the one we really want to focus on, because that one is really the largest driver of what changes are going on in electronics. Yes?
For the ELV, that's the end-of-life vehicles, this is basically just the vehicles which are basically are scrapped and so forth, and then what's it?
Well, there were restrictions on some materials, such as lead, cadmium, for example, but it also deals with the recycling of these materials. Yeah. Yeah. Every one of these programs, incidentally, because we could spend an hour talking about the details, so we're just going to focus on one. And if you look at these programs as a whole, you can see what the European Union is actually trying to do. They're trying to control hazardous substances all the way from product design through procurement and manufacturing, end of life. And therefore they want to collect, reduce, reuse, recycle, etc. And they want to make this an entire loop to minimize the hazards of these various substances. So the ROHS program itself, as I said, became effective in 2006. There are 6 substances that are regulated under this legislation. There could have been more, probably will be more in the future, but 6 are the focus for the legislation or directive in effect today. It's also linked to the Wii Initiative for recycling. And one of the interesting issues of this is that there is an issue of enforcement. And we'll talk a little bit about that as we get into the ROHS initiative. So what are the 6 substances? Well, lead is at the top of the list. Well, we already know about lead, don't we? We know that it was taken out as an additive to gasoline. That's been removed. It's been taken out of paint. Incidentally, how many of you know that in 2009, that automobiles in California can no longer have lead weights on the wheels for balancing? So lead is a bad actor. Unfortunately, you can't really get rid of it for some applications, but it's being reduced. Mercury, I remember as a kid breaking thermometers and playing with the mercury. I now know from ROHS that was bad. Shouldn't have been doing that. Cadmium. Cadmium is a very bad acting substance to the body. And what's interesting about ROHS is you can see on all of these materials except for cadmium, 1,000 parts per million is the allowable limit. These substances must be below that. Hexavalent chromium, this is chromium in the valence 6 state. There's another state, valence 3, which is more benign than the valence 6 state, and it's used in conversion coatings on metals for protection. And in fact, Mike Powers, who's sitting in the audience from Agilent, had the responsibility for the elimination of Chrome 6 in conversion coatings at Agilent. So that's pretty much done. And then there are these polybrominated biphenyls and diphenyls. These are flame retardants. They're used in things like the coating on cables, wire used for wiring electronics. They have been used in the past as a flame retardant in clothing, especially children's clothing. And they have deemed to be not allowable, and so those have been restricted. So those are the 6 substances that we're talking about. Now, quite frankly, the last 2, these have been pretty well removed. We're not going to be concerned about these for the remainder of the talk. We're going to focus on these. And lead is primarily the really important one.
Why is lithium not in that list? Any reason?
Well,
It's so highly reactive.
keep in mind, go back to the original question I asked when I talked about regulation in general. How do you determine what you're going to regulate? If you sit down and list everything that's a candidate, it's huge. Only a few of these are going to make it and have a chance of really being implemented in a reasonable amount of time. Now, there'll be a ROHS 2 and probably a ROHS 3, and things will be added to this. But these were the ones that made the first cut, quite frankly. So there's more to come. So ROHS, that is, these 6 substances pertain to the following items: household appliances, information technology and telecommunications equipment, consumer equipment and consumer appliances, lighting equipment, electrical and electronic tools, etc., and automatic dispensers. Also toys, don't forget toys. Sporting equipment. Okay, there are 2 categories that were not made active in 2006. And those are still under consideration for perhaps becoming active or under the directive of the 2002-95 EC directive in starting in 2012 or perhaps later. That's still being debated right now. Medical devices, monitoring and control instruments, which is what Agilent's concerned about. We make monitoring and control equipment. So that's where we come in. We're presently trying to bring our instrumentations under ROHS compliance a year before this date, quite frankly. Now, there's a lot of work to be done. I have found that some of the medical equipment companies have actually are just starting on ROHS conversion for compliance. They're a little bit behind, and one of the arguments has been, but we don't know a lot about lead-free solders or some of the substitutes that we have to bring into play in these products, and therefore reliability may not be as good, and nobody wants an implantable medical device that's not as reliable as absolutely possible. And that's one of the arguments of I should be exempt.
Yeah, essentially,
Yeah.
still for thermometer we are using Mercury, and then also for, shall we say, blood pressure, measurement of blood pressure, and so on, this column of things. For those, well, they are used, and they are basically the thing that they
Yeah.
Now, for those, are there any restrictions?
There are exemptions. There are exemptions for some things that have been granted where there is no other way to do it.
I see.
Okay, or at least we don't know another way to do it. Okay, so that actually is a good lead into this. You can be ROHS compliant, compatible, meaning compatible means that you have to be able to withstand all the processes that are involved in, say, lead-free processing. And you can do it without exemption and be completely clean, or with exemption. And it's also possible to be ROHS compliant, meaning none of those 6 substances are present in quantities above the minimum viable or minimal minimum concentration levels. But it may not be compatible because it can't be subjected to the high reflow temperatures that a lead-free board would see going through the reflow when the components are attached. So just to give you an example of some of the exemptions, and incidentally, lead acid batteries are not forbidden, but they must be recycled. So there's an exemption, but that's not under ROHS at this point. Okay, so for example, one of the exemptions is that in, say, flip chip on, say, an integrated circuit, you put solder balls on it, you turn it over, flip it over, and you attach it to the package. It turns out that you want a higher temperature solder to do the solder balls on the flip chip. So they have made an exemption. They allow high lead solders to be used. And in fact, 90-10, 90% lead, 10% tin. 93-7 is also used for flip chip. So there's an exemption. Another one is lead in solders to do a viable interconnect. Here's an example of a flip chip on a package. You see the solder balls of a BGA around that, but the chip itself is actually put down upside down with solder balls with high lead. So there are exemptions that have been allowed, and there actually are 29 exemptions right now that are active. Okay, and I'll just say one thing about the Wii Initiative. What I think is kind of interesting about Wii is these are the targets for materials in the European Union. They wanted to recover a minimum of 80% of materials under the Wii Initiative, anything that falls under Wii. They wanted to recover those, where largely that was reuse or recycling of materials. Only 5% was supposed to be allowed for incineration, and disposal, maximum 20%. Now, it's kind of hard to get numbers, but they actually haven't hit these numbers yet. They're probably about 70–80% of the way to actually meeting these numbers. So it's difficult. Even in Europe, where they're very conscious about recycling, it's difficult to make these numbers, quite frankly. Okay, so now let's talk a little bit about the substances themselves. Lead, mercury, cadmium, and chrome. And that's the periodic table, as you will recognize. And lead is really the bad actor. That's the one that's causing most of the issues in the conversion. And so I always wondered where PB came from. It's plum bum. It's from the Latin.
Yeah.
I'd always felt like we should have kept that name. I kind of liked it.
Plumbing.
Yeah, exactly right. Yeah. One of the things that's interesting about lead is that lead poisoning was actually documented in ancient Rome, Greece, and China. This is not a new phenomenon. It's been around a long time. But as I said, it's already banned from paint, pencil lead, gasoline additives, and that type of thing. You can see the world uses most of the lead in lead-acid batteries. And it turns out that only a very small amount of lead is actually used in electronics, quite frankly. But it still is an appreciable amount of lead. And you can see the health concerns. One could actually spend a lot of time going through all the health concerns of lead. There have been a lot of problems documented. And this is just a sampling of the types of problems that you can run into with lead, affecting the nervous system, for example, the reproductive system, etc. So lead is pretty widely banned for a lot of things, except where with a lead-acid battery you really don't have a choice. But recycling is the approach there. Okay, just a little bit about how lead actually gets into the environment and how it would get into a water supply. So let's say that one of these lead weights from a wheel falls off on the side of the road, or a fishing weight is left on the bank, or somebody took their tin lead soldered board and left it in the landfill. Lead oxidizes. Okay, so if you take lead oxide, which you're going to have on the surface of that lead, and you have something like acid rain, which generates all of their weak acids, they're still acids, you can get these water-soluble compounds, these salts of lead. chloride, sulfide, etc. And that can leach into the underground water. It's water soluble. And as that underground water is either taken up for drinking or gets into lakes and streams, that's where it causes problems for humans and animals. So that's the cycle of getting lead into the environment. Mercury. Well, again, we all know a little bit about mercury. It's we've all probably noted it's a really neat liquid metal at room temperature, but it has a lot of problems from mercury poisoning. Again, it's a heavy metal ion, and it can cause problems. It's used in a lot of places: thermometers, barometers, jewelry. I thought this one was kind of interesting. It's an additive to vaccines, such as the vaccine for hepatitis B. Avoid bacterial contamination. Button batteries. How many have we seen those? I actually brought a couple of button batteries with me. Switches, mercury switches, those kinds of things. So it's pretty prevalent. Chrome 6. Okay. This one is fairly famous because most of you have heard the name Aaron Brockovich. And this little town, Hinckley, in California. So the Chrome 6 level in the groundwater of Hinckley was 6 times higher than what the EPA actually considers to be safe. And again, you see it's actually used in a lot of places, but the main one we're concerned about are these conversion coatings on mechanical parts that we put into our instruments. And even my understanding, Mike, is on conversion coatings, even though you've gone through the process, you still have some of the Chrome 6 atoms or ions around in the Chrome conversion coating. And those, under moisture and humidity, can actually leach out. And so that's where your source of Chrome 6 actually comes from when you've that is, done a conversion coating on these materials. So,
is that the same material that is used for tools? The ones that they mentioned that they have chrome as a non-rusting factor?
yeah, I know what you're talking about. I'm not absolutely sure. I'd have to check on that.
That chromium is in a valence 0 state, so that's chrome 0.
So then it's okay.
Not toxic.
It's okay. Yeah. And the valence 3 state also, which is the preferred method to do this now. Okay, so, and I'm not going to say much about the polybrominated materials. They're not a big problem for us, quite frankly. They've been largely eliminated. And okay, so let's talk about homogeneous materials under the ROHS program. So ROHS says that for a material in your product, a homogeneous material, I'm going to define that, you cannot exceed this 1,000 parts per million for any of these materials, or 100 parts per million for cadmium. So if you look at an integrated circuit, this is a plastic encapsulated integrated circuit. It's on a lead frame, which is a metal, and it may have been plated. You can see wire bonds from the chip. The chip might be silicon, for example. And then, of course, you have this molding compound. So each one of these specific materials must meet the criteria for those concentration levels for the 6 substances. That's the way ROHS is defined. There have been people that have said, well, you know, maybe if you just take the component and grind it up, and if the whole thing together is less than 1,000 parts per million for all of these, that's okay. Well, no, that's not what the ROHS directive says. It says that it must be for each specific homogeneous layer or region of that material. And that actually has been confusing for some people, so I wanted to define that. Okay, so how might you detect the presence of such substances? Well, a very simple way to make a first attempt at identification would be one of these handheld X-ray analyzers. This is X-ray fluorescence. And these are actually pretty neat. Here's a little gun It generates X-rays, and it actually looks at the X-ray form. I mean, it looks at the radiation coming back, the fluorescence of the atoms in the material, and it is able to identify these by energies or wavelength, and then a computer attached to this will do the analysis. Now, it's not highly accurate, but it actually gives you a pretty good indicator if a substance is present. And we have evidence that it actually works. Okay, now if you need to know it a little more accurately, then you get involved in some much more comprehensive analytical tools. For example, with these polybrominated materials, gas chromatography coupled with mass spectrometry is a tool that works quite well for that. That's basically they're hydrocarbons with bromine added to them. So gas chromatography is quite effective there. If you're looking for mercury or lead or cadmium, then using various combinations of atomic absorption or emission spectroscopy, mass spectrometry using something like inductive coupled plasma or glow discharge, or other ways such as laser ablation, what you're trying to do is create ions, individual ions from the material. And obviously you can I think, appreciate that if you're taking a material and you're tearing out atoms and ionizing them and running them down a mass spec to analyze it, you have to have calibration standards to go along with that. So it takes a fair amount of effort and calibration to come up with fairly accurate determinations of these. But there are analytical tools to do this.
But these are destructive, I suppose. These are destructive means, right?
Mm-hmm.
Yeah.
So that could be another talk into itself, quite frankly, because there are a lot of very interesting aspects to this. Okay, now let's talk a little bit about how lead-free solders impact electronics. And this is where the elimination of lead becomes very prevalent and has caused a lot of work to be done. Incidentally, this is kind of a typical RF board, a printed circuit board with a number of components. This is a board that someone put together just to do solder testing with lead-free solders. And so they have a number of test packages on here. They've replicated it, and this board can then be put into a temperature chamber and temperature cyclone, or it can be vibrated, can be exposed to shock. There are a lot of things you can do with it. Okay, so before we actually get into some of the details, let's talk about the life cycle of solder. So when you go to solder a component on one of these boards, and actually I'll pass this board around. This is pretty representative of a large number of components, different types of components. Incidentally, the connectors, the plastic connectors are put on after the reflow process. Those are hand-mounted. But the semiconductor parts and the small chip components, resistors and capacitors, of course, go through the reflow. So what happens is you raise the temperature on a board with components on it, with solder paste that having been used. By applying it to the board, then you put the component where the solder paste is. Once you get up to the temperature where the solder begins to melt and becomes a liquid, this is when things really start to happen. And so for example, on the board you may have copper traces, you may have nickel-plated traces, you may have electroless nickel with a flash of gold on it to reduce the oxidation of the nickel. A lot of different things can be put on that board, but the main point is that when that solder melts, materials such as copper and nickel and gold start to dissolve into the solder. And that actually, this dissolution begins the process of where intermetallics can form. Compounds that are not one, such as nickel and tin together may form intermetallics, or copper and tin. So this intermetallic formation turns out to actually be quite important. It's true the intermetallics are weaker than the solder and are detrimental from that standpoint, but without the formation of the intermetallics, you're not going to get a good solder joint. So you can't live without them, and you can't live really with them if they're too thick or too dense. So Then you start to cool the solder, and these intermetallic compounds are forming as you cool. Now it turns out that the solder joint is really in a metastable state, because once the solder is solidified, that doesn't mean that things won't continue, such as intermetallic formation, because if you temperature cycle the board, you will continue to get intermetallic growth and other things that we'll talk about. And then when under use, you'll have various thermomechanical stresses, such as you turn the instrument on or off, or whatever the product is. It heats up, cools down, heats up, cools down. You're temperature cycling it. If you have a cell phone and somebody takes out their cell phone and they drop it, that's thermal shock. I mean, not thermal shock, but mechanical shock. And it's amazing how many cell phones don't survive either being dropped or thrown. So that's an important consideration. So this is the life cycle that we want to keep this in mind as we go on from this point on. And of course, what we're trying to determine when we do reliability testing is how much stress can we have to apply to get a failure. And a failure can be a solder ball that cracks. In other words, you get a separation of the joint. You can have various fractures, resistance increases, that type of thing. So, okay. So we now know that we have to get rid of the lead in solder. There are a lot of candidates. There were probably well over 100 candidates back in around 2000 that people started to think about for replacing lead tin solder. Lead tin solder is a wonderful material, quite frankly. It melts at 183 centigrade. It's quite ductile and malleable. It's a eutectic melt. It's this combination of lead tin was really almost ideal for a solder, quite frankly. And we had about 60 or 70 years of history with it. So we knew a lot about it. We knew a lot about the reliability. So if you're going to change to a different solder, you're starting over. That was the challenge. So a lot of people looked at this, a lot of work. In fact, there are a lot of solders. I don't know how many solders there are, but there have to be an incredible number of solders, combinations. And what we've largely, but not exclusively, come up with, or what we're now using, is this so-called SAC 305. It's 96.5% tin, 3% silver, half of 1% copper. And that is the solder that I think the majority of people are using now. There are other variants of the SAC solders where you might have 4% silver, or you might have 1% silver. And the amount of silver that you put in there can affect the intermetallic growth, and it may, for example, by reducing silver, you may actually get an improvement in the shock tolerance in these solders. So, okay, so I've just kind of summarized what I've said here. There were a lot of nice things about lead tin. It would melt at a lower temperature. It was a fairly ductile joint, so shock and vibration was very robust. Tin whiskers. How many of you have heard of tin whiskers? Okay, tin whiskers I think are one of the neat things. But tin whisker, it turns out the lead in this lead tin solder greatly prohibited. Didn't completely eliminate, but really inhibited tin whisker growth. At the end of this talk, we're going to talk a little bit about tin whiskers. The lead suppressed the copper-tin reaction, that's the intermetallic formation. And like I said, we have 60-plus years of experience with it. So we're going to talk now about this SAC 305. So some of the consequences of this are that the reflow temperature, when you take that PC board and you reflow it with the components attached by solder paste, you're going to do the surface attach to the components, you go to higher temperatures. Well, some of the boards, like FR4, didn't take the 260C very well, and so some new laminate materials, PC board materials, have had to have been introduced. That's probably not a bad thing. The other components, because they're now stressed at a higher temperature, these components have to be able to take the higher temperature over a few minutes without degrading or failing. We now have increased risk of tin whisker growth. The surface finish changes because of microvoids on the surface of the SAC 305 solder. And you have to kind of get used to that, because when you soldered with lead tin, you got some very shiny, very nice joints. You know, I think we all look at a joint and we say, oh, that looks like a really nice, smooth, shiny joint. And we would judge the quality of the joint by its appearance. Well, the SAC solder will fool you on that. It doesn't look as nice. And then, of course, as we said, it's not as good in shock and vibration. The reliability models are just starting to, people are looking at those things and generating data. It takes a lot of data to come up with good models for reliability. Okay. So this is the corner on the phase diagram where this point is 100% tin. This is the percent of copper in the SAC alloy. This is the percent by weight of silver. So we said for SAC 305, we had 3% silver, and we have about 0.5% copper. So this is where that would appear on this phase diagram. Now, what this would really like to be is at this intersection of all of these lines, it's about SAC 3.8 or 388, actually, the way we would read that off. So you see it's a little higher in silver, a little higher in copper. At that point, at 217 C, that's the liquidus temperature. The SAC 305, you actually have to heat up a little higher because it's a little different composition. You actually have to heat that to a little higher temperature for it to actually turn to a liquid. But now as it turns to a liquid, and as a liquid, it can start to have dissolution, and it actually can start heading for this point. My point of this slide is there are two things. One is, for example, SAC 105 is one of the solders that people are using for more robustness in vibration, for example. This one, you can see you have to heat to a fairly high temperature, probably about 226, before it becomes a liquid. If you make a SAC alloy solder that's way off on either side of this tin-rich segment, you can see you can actually have to increase the temperature to turn it into a liquid by quite a bit. The other part of this is when you buy a SAC 305, it isn't necessarily 3% and 0.5%. It's probably close to that, but there's some manufacturing variability. So you have to build tolerance into your process. You can't just believe these numbers straight away. Okay, oops. Okay, I did want to say a little bit about tin, because you'll note in the SAC solders, tin is dominant. It's 95, 96, toward 97% tin. So we really have a tin-rich material. Tin plays a big role in the intermetallic formation and the behavior of this material. So tin is obviously a nice choice because it has a low melting temperature. Tin itself melts at 232. It's widely available, low cost, environmentally benign. That's really the main thing here. It actually is a pretty good electrical conductor. It has good wettability. One of the things I thought was interesting is tin was actually first used to harden copper to make bronze 3500 BC. That's a long time ago. This is not a new material. Copper isn't a new material either. Okay. And you can see that in terms of the world consumption of tin, as of 2006, the estimate was that solder consumes about a half of it. That's a lot of solder, 188,000 tons. So one of the things that I would point out is when you turn this material into a liquid, when you start to cool it, you can get intermetallic formations such as silver 3 tin or copper 6 tin. This is where copper would start to play a role. If it's on a copper pad, you'll get even more copper. So now you have competition for these intermetallics being formed. The beta tin is the pure tin. And when solder cools, it isn't homogeneous. You get regions of intermetallics, you get regions of various compositions and materials. So depending upon what you dissolve in this solder joint while it's liquid can have a very interesting effect on its behavior, such as wetting. Well, tin coatings behave differently than the old lead tin coatings. For example, people used to solder dip leads on components. And so finishes on leads is very, very important. Choice of flux. I'm not going to talk about flux, but the choice of flux can be very, very important here. Component finishes, as I said, are very important. Surface cleanliness, free of oxides, etc. Use the correct temperature profile, otherwise you can run into trouble.
Don, is wetting is it the lead or the solders?
Yeah, if I have a pad, and I want solder to cover this entire pad, and there's a component that's adjacent to it, then what I want is for the solder to cover all of that pad. Now, if the pad isn't clean, it may retard. But I want wetting. In other words, I want the intermetallics to start forming over this entire pad as I cool it. So yeah. And sometimes with lead-free, you don't get that. Okay. Here are some examples of what you would see. Now, on the left-hand side, this is lead tin solder. So here's a cross-section of an IC package with the lead coming down. And you can see that looks like a pretty good solder joint, doesn't it? If you look at the equivalent joint with SAC 305 solder, it doesn't look quite as shiny and smooth, does it? Here's just a solder ball, nothing attached to it except it's sitting on a pad. Lead tin, and you get a rougher surface. This is actually pretty good. But some of them look actually worse than this. But the SAC solder looks rougher. You actually get microcavities on the surface of these balls as they cool. Here's a small component on a surface mount board. Lead tin. Now I have to. The lighting's a little different here, so don't look at the yellow color. But you can see the quality of the surface finish, how shiny it is relative to the lead tin. So that's the kind of thing that you typically see optically.
How about the conductivity of these things?
Well, these are actually very good solder joints.
Yeah. I mean, in other words, the resistance is quite good.
Yeah. Okay, so reflow profile when you run a board with components on it into a reflow furnace. What you do is you have a period where you preheat it, you bring it up to, you leave it in for a certain amount of time because you've got a lot of thermal mass on that board. Not all of that board heats up at the same temperature at all time. So you can actually see that once you've preheated the board and the components, then you actually reach the solder melting point. And for the SAC 305, this is 221, as we showed on that phase diagram before. Then there's a short period where you take it up to a peak temperature. This is typically like 260. It's typically like 225 or 230 for lead tin solder. So you can see it's about 30, 35 degrees hotter than with lead tin solder. And then, of course, you cool it down fairly rapidly. It's very important that you don't leave it at this higher temperature for too long, or you'll get perhaps too much intermetallic formation. You get a degraded or weakened joint.
So basically, this high temperature would not destroy the semiconductors.
Semiconductors are pretty good up to about 300. Okay, some general problems. Well, you can have thermal degradation. Tin whiskers we'll talk about in a minute. Delamination. If your PC board isn't able to withstand 260, you can have some really neat things with these layers coming apart. Not good. Warping. I've seen board warping because of the higher temperature, especially if the board is loaded both sides and they're very different. There's something called popcorn failure. Plastic packages, and there's some on the board that I passed around. Here's another one with a BGA and some plastic packages. If there's moisture inside the plastic package and you bring it up to this very high temperature, these temperatures are greatly exceed boiling temperature of water. You can actually get high pressure developed in the plastic because the steam can't escape, and it breaks, it pops open. it breaks the plastic. I've actually seen parts of the plastic come off the package itself. So that's popcorning and some other things. Okay, let me give you an example of where this turns out to be really interesting. So this is a BGA. This is a substrate. Solder balls attach this package to the PC board itself. There's an integrated circuit inside. And there's actually a lot of thermal mass with this package. In fact, some of the board that came around, some of those packages are very large. There's a lot of thermal mass. It takes a while to bring those up to temperature. And in fact, this is an experiment that was published last year where they actually embedded thermocouples in various parts on the package, at the chip, solder ball in the center, solder ball out the corner or the edge, and then at a trace a little far removed. And you can see this was run into a reflow furnace that was set at 260, and out away from the package, indeed, they did actually see 260. 255 at the edge of the package, pretty close to 260. Everything's okay. Whoops, near the center of the package, it only got up to 240. So these solder balls are not all going to, when they go through cool down, they may not all be the same in terms of the cross-section of the intermetallic growth. And also, they're going to freeze, that is, solidify at different times. They're not all going to do it uniformly. Hence, you can see that as you lower this temperature, you can see if it reflowed at around a little over 230, 250, you got a pretty good solder joint. If this temperature is below or too short a time, you actually get degradation in the solder balls. Now, where this has really caused problems is if you have a board, and let's say in this part of the board we had a bunch of BGAs where there's a lot of thermal mass, and down here we didn't. This part of the board will not get anywhere near as hot as it should. There's a mismatch in thermal masses, and therefore when this reflows through the furnace, if you're not careful, you will not get good solder attached with the BGAs. Now, there have been companies, and I will not name them, that have said, oh, we can fix this by dropping the reflow temperature. Let's change it to 270 or 280. Well, there are probably components that cannot take that, and we've seen problems like that. So that's why this becomes very important to know something about the thermal masses on your board. Okay, there are other defects that can occur. This is something called tombstoning, which I think is very interesting. Pretty obvious this is a defect, this is a flaw. And what happened is, you can see, this probably turned to liquid sooner. The surface tension is favorable, and it actually lifted this very light component. So you can see, insulating lead tin, you can also see some tombstoning. It's not just lead-free solders, but it's probably a little more prevalent in lead-free solders than in tin lead solder. So tombstoning can be a problem. If it doesn't get sufficiently hot, you'll get cold joints. And I think we all know what cold joints are in soldering. Not good. Voids, voiding can occur in solders, and that is not good. Pad cratering is another failure mechanism, and this is due to the fact that what you're looking at here is a PC board. This is the surface of it. This is a solder ball up to a component. And what you're actually seeing here is, in this cross-section, there's actually a fracture in the PC board. It's exaggerated here, but you can see what's happened is, when pad cratering occurs with at higher temperatures, you can actually get a separation and potentially a break in the metal line that feeds the signal in or out to the solder ball. Pad cratering, another defect, and it becomes more and more prevalent as you go to higher temperatures in the reflow. So, another example of failure mechanism. that is exacerbated by the higher reflow temperatures. Okay, so let's say a little bit about these intermetallics. And this is a very fascinating subject. One thing I'll point out is what we have here is, this is a copper pad, and we have tin in the solder. Remember, it's a tin-rich solder. And the intermetallics, in this case copper tin intermetallics. What's interesting is all of these materials have different crystal structure. There's no way you're going to get these to match up. And in fact, what typically happens is that as you go into the mill, you get a liquid in the solder, copper starts to dissolve into the solder. In this particular case, where the cross-section was taken, you can see there's a layer. It's a fairly random layer in terms of thickness of what's called the E phase intermetallic, or epsilon phase, of copper 3 tin. Then there's the copper 6 intermetallic. And then finally up here is the unreacted sack solder. Now this was reflowed for quite a long time to make sure that a lot of intermetallics were actually formed here. These are some surface morphology SEM photos for both of these intermetallics, and you can see they're quite different in structure.
Yeah, what's the effect of these different structures?
Okay.
As far as the
Well, what you would be concerned about here is the strength, the physical strength of these intermetallics. The intermetallics in general are always weaker than the solder itself. And you can also get voiding that occurs during this intermetallic formation. Here's an example, the cross-section, where you can see here are the intermetallics. This is actually the lead itself on an integrated circuit. And the lead is bent, so it's a little thinner there. This is intermetallic formation, tin copper intermetallic formation along here. You can see there's a boundary, and you can see there's some voiding that has occurred there. And these intermetallics and the voids will weaken that solder joint. That's what we're concerned about. And so what people do is they try to, they have to have some intermetallic formation. That's why I call this the good, the bad, and the ugly. You want some intermetallics, say typically tin on copper, to be around 1 to 2 microns of intermetallic. That gives good wetting, and it gives a reasonably good solder joint in terms of strength. If it's less than a micron, you probably get a relatively poor solder joint, poor wetting. The bad is intermetallics are very brittle. If they become too thick or too prevalent, you'll have a weak joint. When you start stressing it, thermal cycling it, shocking it, you can have, you can actually get open circuits from that. And then none of these look really neat, so they're all ugly, quite frankly. I guess the material science would say they look beautiful. Okay. Tin whiskers. And I know we have about 5 minutes left, so this is just about on the mark for timing. Tin whiskers are interesting because it turns out that you can get these very small fibers that grow out of tin. And you can see they're typically of the order of maybe 1 to 5 microns of that order. They're pretty small. Some of the longest ones ever recorded were around 18 millimeters, but that's very rare. That's a world record, probably. There is evidence that they have caused satellite, missile, heart pacemaker, and nuclear plant shutdown. In other words, they can have consequences. What do? They short. They can grow and short. They can break off and rattle around in electronic apparatus. So the problem is shorting. And if you get something that's a few microns in diameter, they can carry some pretty appreciable current. So anyway, there's been a lot of interesting discussion in the literature over the last 30, 40 years about the mechanism. And I think this is still somewhat debatable, but the model that I like is that, for example, we have a solder layer here that is tin-rich. It's on copper, and as the copper is dissolving into the tin, we're forming an intermetallic. And at the grain boundaries, we get enhanced transport and enhanced, or we get regions that go deeper into the tin with the intermetallic. These grains of tin then are being pushed on or compressed or squeezed, and you'll have a tin whisker that will squirt out like toothpaste coming out of a tube. Fairly simple model. So it's actually being pushed by compression. And that's the model that I like. I know there are a lot of other models. There are some objections to this also, but it's a fairly simple model, and it seems to be about as good as anything that's been published. Here's an example, a couple of examples of tin whiskers. You can see here we have some leads. You can see the whiskers have grown and potentially can short between leads. Here's a material that where you can see a lot of tin whisker growth has occurred. And one of the things that's really kind of scary about this is I've heard people from jet propulsion labs say that tin whiskers can grow many years after the component was made and assembled. In other words, how do you test for that? That's difficult. So here's some work that was published where they took cross sections. This is actually a whisker. They took cross sections just adjacent to it, and you can actually see where they've identified the intermetallic that's growing, in this case the copper 6 tin 5, and you can see the sequence in the growth here. And as the intermetallic's getting a little thicker, you can see the tin whiskers growing longer. And that's one of the experiments that's been cited for this particular model. So.
Now, can one reduce these things by the temperature or something?
Yeah, anything that would affect the rate of growth of the intermetallic are the variables that you would want to look at. See, one of the things that's confusing about tin whiskers is you look at through the literature, they've looked for things like humidity, temperature, all those things. If you take all the papers and line them up, there's a lot of inconsistency. And that's probably because not all the variables are being looked at, quite frankly. So anyway.
What about informal coating? Would that, at least in the short term?
Well, that's one of the things that's actually been recommended to try and control that to some extent.
What was it? I didn't catch that.
Coatings?
Conformal coatings, the stuff that you have on automobile.
In other words, put a lid on it. Okay, so last slide. We'll hopefully have a little better understanding of ROHS and what the. In other words, to sell into the European Union, you must be ROHS compliant, basically. There are other countries such as China, Korea, California. Schwarzenegger did say this was a country, didn't he? Oh, okay. As I said, ROHS 2 will probably add additional substances to the original 6. Reliability will improve as time progresses. We're in a learning curve mode, quite frankly, at Agilent. Solder development will probably continue, and there could be some very interesting solders that emerge in the future. And finally, there are other programs that are continuing, such as this REACH program. So with that, I'll conclude. We went over a lot of material very fast, but thank you for your attention.
Why do you say that it's extending to other countries and then say California? Is it that it came to California? I mean, usually California takes these.
Well, if Arnold were here, he'd probably tell you, if you look at the gross domestic product of California is bigger than many countries. So.
Exactly. No, I know, but I thought that California.
I'm not saying he's going to secede from the union, but anyway.
I thought that California usually adheres to the regulations more quickly than other parts of.
Typically, it's true. Incidentally, there is a California ROHS, and I did not go into the details because it doesn't work exactly like the European Union ROHS.
It gives you mean more than.
Well, it's not as restricted.
Is it in effect now?
Yes. Well, is it, Mike?
Yes.
It is. Yeah. Okay. Yeah. But you don't hear much about it, therefore it doesn't really have a lot of teeth. Yeah.
One thing I just thought I'd add, because I've run into this in the last couple of days, is that the lead-free parts don't just affect solder. Like, it affects connectors and stuff too, because if you have a lead going into a connector, if it has sharp edges, it no longer bends to
Right.
fit
Yeah.
the whole bit.
Yeah, it has there are a lot of implications and things like that that I haven't brought up at all because we just didn't have the time, quite frankly. It's a fairly complicated subject. Yeah. Yes?
Have you given measurements on thermoelectric voltages with the new solid compounds?
I have not, and I haven't actually read any papers on that. But
There should be a change.
But there is a lot of interest right now in electromigration and things like that. But the voltages that are developed, I don't have any of that data on the top of my head. But I'm sure there are people that have looked at some of that. I just haven't. Yes.
What's a common replacement for FR4?
The what?
For FR4, you
Yeah.
said that it can't take the heat. So what's commonly used?
Well, there are several material boards that are being used. Nelco makes a board. They actually make quite a few boards, but some of them are very FR4-like, but will take higher temperatures. The glassivation temperature is higher, in other words. So, Nelco 12 or Nelco 13, something like that. That's one. There are others.